Hey everyone, this is Ms. Scott here, and I'm going to walk you through some notes on limiting reactant and percent yield. So make sure you have a new page in your notebook. You can title these notes Limiting Reactant and Percent Yield Notes. Okay, and so what we're going to talk through in these notes are a little bit about what exactly is a limiting reactant, how do we calculate it, and what is percent yield and how do we calculate that? How do they relate to the stoichiometric calculations we've been doing in class? So first, let's define these ideas. Okay, so we've got kind of two terms to define here: limiting reactant and excess reactant. Okay, and so if you think about like a recipe, for example, you probably, if you have ever looked at recipes, you'll notice that there are a list of ingredients. They tell you certain amounts that you need. And so if you ever tried to cook something or bake something like cookies, you may have tried to scale up a recipe, so make double the recipe or triple the recipe. You may have run into an issue where you didn't have enough of one of your ingredients. So let's say your recipe calls for 2 eggs and you want to make 2 batches of your recipe, but you only have 3 eggs. And so in that example, your eggs would be your limiting reactant. Okay, so if we think of ingredients like the reactants in our chemical reaction, your eggs would be your limiting reactant. And so that's our first term here. So the limiting reactant is the first reactant that is used up in a reaction. Okay, so for the majority of chemical reactions, you have normally 2, sometimes more, reactants that we start with for a reaction, and they come together to create our products. And so you're going to start out with a limited quantity of both of these for most reactions. And so one of them is going to be used up first. And so when the limiting reactant is all used up, no more product can form and the reaction stops. Okay? So if you only have 3 eggs, you can't double that recipe. You cannot make any more of, let's say, cookies, if that's what recipe is for. Okay, so once your limiting reactant is all used up, you cannot make any more product. So that reaction actually stops, even though you may have some of your other reactants left over. So for my example, maybe I still have butter and sugar, but it doesn't really matter because if I don't have eggs, I can't keep going. I can't keep making more. Okay, so if you look at this visual that's kind of up here in the top right-hand corner, if you think about the amount of reactants you have before the reaction, when they come together, they're going to make some amount of product, and you're likely going to have something left over from one of your reactants. And so my limiting reactant limits how much of the product I can make. Okay, so if I only have my 3 eggs, I can only make 1.5 batches of my cookies as opposed to 2. So my excess reactant is what is ever is left over after the reaction stops. So it's the other reactant. I may still have enough butter and sugar to keep going, and that would be my excess or leftover reactant. And so an important thing to note here is that when we're thinking about chemistry and limiting reactant is not necessarily the one that you have the least of. So let's say you're given 10 grams of hydrogen and 30 grams of oxygen. It is not necessarily that your hydrogen is going to be your limiting reactant, even though you start off with less grams. We need to compare amounts of substance in moles. We cannot just look at this amount in grams. We have to take into account the ratio that they react with each other. Okay, so for example, hydrogen and oxygen are going to react together to make water. However, you need 2 times as much hydrogen as you do of oxygen in order to produce water. Okay, and so we can't just look at the grams. We actually need to first convert them into moles and look at that ratio in which they react with each other to determine which is going to produce less product. Okay. And so another idea, kind of the other thing that goes along with this, are the idea of theoretical, actual, and percent yield. And so notice there are a couple of abbreviations here: TY, AY, PY. So TY is our theoretical yield, AY, actual yield, PY, percent yield. And so our theoretical yield is just the amount of product that should be able to form if all your reactants completely react to form products. And this is what you have been calculating using stoichiometry. This is what we're going to calculate when we're looking at limiting reactants. It's how much theoretically you should be able to make if everything perfectly reacts together. Okay? My actual yield, to contrast that, is what is experimentally determined in the lab. And now this is kind of hard for us considering we haven't spent a lot of time in lab, but if you've ever cooked anything, kind of think about the fact that it's really hard to get all of your batter, for instance, out of the bowl. You're right, some of it gets stuck to the sides. If you're baking a cake or something like that, it's really hard to make sure that you actually get all of the product that you should from your reaction. It's hard to make sure that all of your reactants actually mix together and are able to react to completely form your products. And so sometimes your actual yield is not the same as what you theoretically should have gotten. And so your actual yield has to be experimentally determined in lab. It's specific to one experiment. And it must be given or measured in some way. It's not something you can theoretically calculate. Okay? And so when we compare the two, we're looking at percent yield. And percent yield is a really useful measurement, especially when you're thinking about how well you've done an experiment. Okay? And so our percent yield compares the actual to the theoretical yield. And so you take the actual yield, normally a mass in grams, and divide it by your theoretical yield in grams, and multiply it by 100%. And so the closer you are to 100%, the more accurate you can think of that your experiment was. And so if you theoretically should have made, let's say, 2 grams of water, and your actual yield is 1.98 grams of water, you've done pretty well. And so percent yields tend to, your goal is for it to be about 100%. That means that you got out what you theoretically should have from your reaction. You made as much product as you thought you should. Side note, your percent yield can be more than 100%. And this does not necessarily mean that you've made more product than you theoretically should have been able to. What it normally means is that the product that you have is not pure. It's contaminated with something. Normally that's water. It means you need to dry it and to evaporate that water. But your goal is for your percent yield to be as close to 100% as possible. And that's kind of an indication that you've done a lab well, that your experiment has worked, that you've been careful in your experiment not to lose reactants or products in various places. And again, this is challenging for us this year to kind of think about, considering we don't have that much experience in lab. But just kind of think of any time you've tried to make something in the kitchen and just think about how hard it is to keep track and kind of keep everything clean and neat and everything together. And so that is something that we can calculate in order to kind of tell us a little bit about our experiment. It is easily confused with percent error. Okay, and your percent error is this calculation down here at the bottom, and it is not comparing. It is more comparing an experimental value that you get in lab to a theoretical value for something that that we kind of assume to be true. Okay, and so it's measuring how far away is your value from what it theoretically should be. Okay, and it's a different measure, and it's actually, if you look, it's the theoretical value minus the experimental value over divided by the theoretical value and the absolute value of that. And so this might be more applicable if you're looking at, let's say you do an experiment to calculate the density of water. There is a theoretical value for the density of water, which is 1.00 grams per milliliter. In your experiment, let's say that you calculate it to be 0.98 grams per milliliter. And so you could get a percent error value to look at how close your experimental value came to the accepted theoretical value. Okay, and so that's a different measurement, just not to get confused between those two. So let's go through one example of how to calculate the actual yield of an experiment, or the theoretical yield of an experiment, how to figure out what your limiting reactant is, how to figure out how much you have left over of your excess reactant, and how to calculate a percent yield. Okay, so we're going to do this example. So I would pause and make sure that you have this written down. So we're going to go through each of these steps together. Okay. And so the example we're going to do together is 4.00 grams of lead-2 nitrate are added to an aqueous solution containing 1.00 grams of potassium iodide. So the first thing we need to do is write a balanced equation for this reaction. Then the second thing we're going to do is determine how many grams of PbI2, so lead-2 iodide, precipitate is formed in this reaction. And then we're going to look at how much reactant is left over. So after we determine how much is formed and which one is our limiting reactant, we're going to look at how much we can have in excess. And then if 1.00 grams of PbI2 was actually produced in the lab, what was the percent yield of this experiment? Okay. So our first step is to do part A, which is to write a balanced equation for this reaction. So take a moment, pause the video, and if your reactants are lead-2 nitrate and potassium iodide, predict what your two products of this reaction are going to be, and write a balanced equation for the overall reaction. So take a moment, pause to do that. So what you should get is lead-2 nitrate should be PbNO3 is added to an aqueous solution containing 1 gram of potassium iodide. So potassium iodide is Ki. Both of these are aqueous. These are going to be aqueous solutions. And they're going to form together to create PbI2, which is going to be our precipitate, our solid. It's going to be lead-2 iodide. And potassium nitrate, which is going to be aqueous. Remember, nitrates are aqueous. And so to balance this, we can put a 2 in front of the KNO3 and a 2 in front of the Ki. Now we have a balanced chemical equation. And so we're going to use this to calculate how much PbI2 is being produced. And so one of the things you can notice here is that instead of being given just information about one of your reactants, you're given information about both reactants. And that's kind of your indication that you need to determine which one of them is the limiting reactant. And so let's think about this second question. How many grams of PbI2 precipitate are formed? And so there are two different ways that you can calculate this. And so this is actually your theoretical yield. This is us calculating our theoretical yield. Okay. And so there are two different ways we can do this. We can do method 1 or method 2, and we'll go through both of them. For practice, you're going to need to try both of them, but you can kind of then, from then on, figure out which one works better for you. So method 1 asks you to compare reactant amounts. So you're given an amount of each of your reactants, and so you're going to choose one of them and determine how much of the other reactant is required to react with all of that first reactant. So you're going to determine how much potassium iodide, Ki, is needed to fully react with 4 grams of lead-2 nitrate, or how much lead-2 nitrate is needed to fully react with my 1 gram of potassium iodide. And so we're going to compare the actual amount of reactant B to determine if it's limiting, use limiting reactant to determine how much product can be formed. Okay, so once we figure out which one is our limiting reactant, which one are we going to run out of first, we can use that reactant to determine how much product can be formed. So this is method 1. Method 2 is where you're going to compare possible yields. So you're actually going to do 2 stoichiometry problems here. You're going to determine how much product each of my reactant would be able to form if I had an unlimited supply of the other reactant. So how much reactant or how much product could be formed if all 4 grams of lead-2 nitrate reacted I had an unlimited supply of potassium iodide. And how much reactant or how much product could be formed if all of my 1 gram of potassium iodide reacted completely. Okay? And so the lesser of the two is the amount of product that could actually be formed. And the reactant responsible for that is the limiting reactant. But the main thing to know is that when I'm determining how many grams of PbI2 precipitate is formed, that is based off of the limiting reactant. Okay? And so let's take a look at actually this first method right here. Okay, so we're going to go through both methods for answering this question. So method 1 is to compare the reactant amounts. And so I'm going to do my best to do this on screen. Okay. And so what I'm going to do is I'm going to say, okay, how much, let's just say potassium iodide is needed to fully react with 4.00 grams of lead-2 nitrate. I have all my molar masses up here. I have my balanced chemical equation to help me with my mole ratios. And so I'm going to start off by doing 2 stoichiometry problems. Okay. So I'm going to start with my 4 grams of PbNO3, my lead-2 nitrate. And my first step is always I need to make sure that I know how many moles I have. So my molar mass of lead-2 nitrate is going to be 331.22 grams per mole. So that 331.22 grams of PbNO3 be on the bottom, and 1 mole of PbNO3 is going to be on top. My second step is I know how many moles of PbNO3 I have, but I want to know how many moles of potassium iodide are needed to react with that many moles of lead-2 nitrate. So I'm going to use my mole ratio from my balanced chemical equation. So I'm going to put 1 mole of PbNO3 on the bottom. I'm going to have 1 mole, or actually I take that back. I'm going to have 2 moles of Ki on top, right? Because I have a 2 in front of here for potassium iodide. And then my last step is I need to figure out, well, how many grams actually is that? Because I have 1 gram of potassium iodide. I need to know if that's enough to react with all 4 grams of this lead-2 nitrate. So on the bottom, I'm going to have 1 mole of Ki, and I'm going to use the molar mass of potassium iodide, which is 166 grams per mole on top. And so if go through, cancel out all my units, put this in my calculator, what I'm going to end up with is 4.01 grams of Ki. So I need 4.01 grams of potassium iodide to fully react with my 4 grams of lead-2 nitrate. Problem: I only have 1 gram. So I actually don't have enough. I don't have enough Ki to fully react with 4 grams of lead-2 nitrate. And so I could stop here. I've actually answered my question about thinking about just how much potassium iodide I need to react with lead-2 nitrate. But let's just look at our other reactant. Let's start with our 1 gram of potassium iodide, and then we'll figure out how many grams of lead-2 iodide I've actually can form. So let's instead just ask the question, well, what if I said, okay, I have 1 gram of potassium iodide, and I want to know how many grams of lead-2 nitrate are necessary to react with all this 1 gram of potassium iodide. So I'm basically going to do the opposite stoichiometry calculation. So I'm going to first convert my grams of potassium iodide into into moles of potassium iodide. And then I want to think about, okay, how many moles of PbNO3 do I need to react with this many moles of potassium iodide? And so that's going to be a 2 mole of Ki on the bottom and 1 mole of PbNO3 on top. Again, that's my mole ratio coming from my balanced chemical equation. And so my last step is to figure out, well, how many grams is that? So I'm going to have 1 mole of PbNO3 on the bottom and 331.22 grams of PbNO3 on top. And so if I go through and calculate this one, what I'm going to get is going to be 0.998 grams of PbNO3. Now, what do these two numbers tell me? what these two numbers tell me is that I need a total of 0.998 grams of PbNO32 to fully react with my 1 gram of potassium iodide. I have 4 grams, so I have more than enough lead 2 nitrate. However, to fully react with my 4 grams of lead 2 nitrate, I need 4.01 grams of Ki. And I don't have that. I only have 1 gram. So I'm like almost 3 grams short. And so what this tells me is that my limiting reactant is my Ki. I don't have enough potassium iodide. So Ki is going to be our limiting reactant. So I'm going to write ALR as to indicate that's my limiting reactant. And so I can use the fact that Ki is my limiting reactant to determine actually how many grams of PbI2 I'm going to form, because potassium iodide is going to be what is going to run out first. So that's what I need to start with. So I'm going to start with my 1.00 grams of Ki. I'm going to first convert again to moles, because that's going to be my first step every time. And so I have 166 grams of potassium iodide for 1 mole of potassium iodide. Next, I'm going to use my mole ratio between the two. So I have 2 moles of Ki, and I have 1 mole of PbI2. Okay. And now I can figure out how many grams of PbI2 can be made. That's up here. So I know that 1 mole of PbI2 is going to be 461 grams of PbI2. And so if I calculate this out, what I'm going to get is 1.39 grams of PbI2 that can be made. Okay, and so the amount of PbI2 that can be made is based on the limiting reactant. Okay, it has to be based on my limiting reactant. And this is my theoretical yield. Okay. So this is how much I should be able to make if I react 4 grams of lead 2 nitrate with 1 gram of potassium iodide. All of my potassium iodide is going to be used up to make 1.39 grams of PbI2, and I'm going to have some amount of lead 2 nitrate left over, and that's what we're going to calculate next. Okay? So this is method 1, comparing reactant amounts. What I'm going to do is I'm going to show you method 2. Now, we already know the correct answer, but the point is to see the other process for getting to this answer. Okay? And so some of it's going to look similar and some of it's going to look different. Okay? So we've calculated in this example, we've figured out what our limiting reactant is and what our theoretical yield is. And if you missed anything from that slide, it's all right here. Okay? So let's look at method 2. What's the other way of determining my limiting reactant? And so method 2 is comparing possible yields. So what you're going to do for method 2 is you're going to basically just assume that you have some amount of one of your reactants and an unlimited amount of the other reactant, and determine how much of your product could be formed, and whichever one has the least amount of product produced, that is going to be your limiting reactant. So let's start with our 4 grams of lead 2 nitrate. So again, first step always is to convert to moles, right? If I have grams, I need to be in moles. I cannot compare the mass of two things. And so that's going to be 331.22 grams of PbNO3. Okay. Next, I'm now looking, instead of at my other reaction, I'm looking at my product. So I want to know how many moles of my product to be formed and how many grams of my product to be formed. So 1 mole of PbNO3 can produce 1 mole of PbI2. Even though this is a 1-to-1 mole ratio, you still need to include it in your work. Okay. And my last step is to say, well, I actually really want to know how many grams that is. And so 1 mole is equal to 461 grams of PbI2. And so if all 4 grams of my PbNO3 reacted with as much potassium iodide as I needed, then that would make 5.51 grams of PbI2. Now, let's look at instead my 1 gram of potassium iodide. We actually did this calculation in our other method. And so we said if we had 1 gram of potassium iodide, how much lead 2 iodide could be formed. And so this was 1 mole Ki is equal to 166 grams of Ki. And using my mole ratio, that's going to be 2 moles of potassium iodide will create 1 mole of PbI2. And 1 mole of PbI2 is 461 grams of PbI2. Notice it's very similar across these, right? These are even the same last step using our molar mass, mole ratio, molar mass. Okay? And so if I calculate this out, I'll get 1.39 grams of PbI2. So for method 2, what I'm doing is I'm assuming that basically I'm taking each of my reactants and assuming I have as much as I need of the other reactant and determining the maximum amount of product to be made. Now, what this basically says is that 4 grams of lead 2 nitrate could make 5.51 grams of lead 2 iodide. 1 gram of potassium iodide could only make 1.39 grams of lead 2 iodide. And so the lesser of these two amounts, which is this one, that is my theoretical yield. That is what actually could be theoretically made in this reaction. All right? I can't make 5.51 grams of PbI2 because I don't have enough Ki. It can't make that much. If all of this reacts, it can only make 1.39 grams of PbI2. That's it. That is the maximum that can be made. Those other, 4 grams or so, they're not possible to be made. Okay? It's like saying I don't have enough eggs to make those 2 batches of cookies. I only have 3 eggs and I need 4. So I can't make 2 whole batches of cookies. Okay? And so what this means is whichever reactant gives you the smaller mass, the smaller theoretical yield, then that is your limiting reactant. Okay? And so Ki here is my limiting reactant. And that's the same thing we found with method 1. Both of these methods will get you the same answer. Realistically, for method 1, you only need to do one of those first 2 conversions that I did. And so both of them really take 2 stoichiometry problems to do. And they both give me the same 2 pieces of information. They give me what is the limiting reactant and what is your theoretical yield. You just need to determine which one makes more sense to you and which method you feel more comfortable using. Okay? And so again, these are on the slides. Okay. And so what we've learned by both of these methods is that 1.39 grams of lead 2 iodide is our theoretical yield. That's how much can be formed. And that Ki is my limiting reactant. Potassium iodide is my limiting reactant. And so what that means is that my excess reactant is lead 2 nitrate. And so what I can determine is how much reactant is left over. Okay, and so I'm given 4.00 grams of lead 2 nitrate. And then in my first calculation, if I use method 1, what I determined was that if all of that 1 gram of my potassium iodide reacted, then I would need 0.998 grams of lead 2 nitrate. Okay, so this is actually a calculation that I could have already done in method 1. Okay, and so this is saying, well, if you have 1 gram of Ki, how many grams of PbNO3 did you need? And now if you did method 2, you would actually probably need to do this calculation. You would need to determine how much of your reactant is needed to fully react with your limiting reactant. Okay, and so if I'm given 4 grams, I can subtract the 0.998 grams that were being used. This would get me 3.002 grams, but based on my sig figs, this should only be, right, 3 sig figs. And it should only actually be, more appropriately, this should be 2 sig figs after the decimal point, because this is a subtraction. Okay. And so 3 grams of my lead 2 nitrate are going to be left over. Okay. And so our last step is to figure out, well, what is our percent yield? So we were given some lab data, and we know what our theoretical yield is. That was 1.39 grams of lead 2 nitrate. And so now we just need to think about our theoretical yield. And so our percent yield. And so our question was, if 1 gram of PbI2 was actually produced in the lab, what was the percent yield of that experiment? Well, the formula is actual yield over theoretical yield. Oop. And so my actual yield is what I'm given in this problem here. I'm given information that I made 1 gram of PbI2 in that lab. And so that's what goes on top. And then my theoretical yield is what I calculated, okay? This is what we calculated using my limiting reactant, okay? And it's what I expected to be able to make. And so if I divide 1 by 1.39 times it by 100, I'm going to get 71.9%. I only made 71.9% of what I thought I should have. So probably should go back and look for some of that lost product. Okay. And so this was a kind of step-by-step walkthrough of how to approach limiting reactant problems, okay, and how to determine what the limiting reactant is, what your theoretical yield, how much you can actually make, and how to calculate percent yield in excess reactant, how much is left over. And so what you're going to do for homework is look at kind of 4 practice problems and work through the same kind of steps that we did, okay, of determining what is your limiting reactant, determining your theoretical yield, and determining your the amount of excess reactant left over, and a kind of percent yield calculation based on some lab data given to you. Okay, there is a video here that you can go through that kind of gives another explanation of how to think through these problems. For the first 2 of the problems, you're gonna kind of prompted to use either method 1 or method 2, just to get you comfortable trying them both out. And then for problems 3 and 4, you may use whichever of the methods make more sense to you. Okay, make sure to label all of your units box answers and include explanations for reasoning when it's asked. Okay, thanks for kind of hanging out with me and going through limiting reactant practice. If you have questions, make a note of them and ask them during class.